Hello, welcome to the online certification course on deep learning. So, we are discussing about the backpropagation learning algorithms with some examples. In the last class, we have taken an example at the network level, that is, given a feed-forward neural network, how to compute the error at the output node, and then how do you propagate that error in the backward direction from output towards input layer, and as you propagate the error from output layer to the input layer, how the weights in every layer are updated. The whole purpose of this backpropagation algorithm and weight updation is that we want that output error, that is the difference between the actual output that you get from the network and your target output, that should be minimized. So, in the previous class we have discussed this with respect to a network in the network level. Today's lecture we will see that the same backpropagation or the gradient propagation is applicable within a node itself, because every element in a neural network is nothing but a neuron or a node, and within the node, as the complexity of the node increases, the node may also consist of a number of layers. It is not necessarily that every node will compute in a single layer fashion. So, I can have multiple layers within a node, and today we will see that how this gradient can flow within a node from output of the node to the input of the node. So, before we go into that, let us just try to recapitulate what we have done in the previous class. So, in the previous class we had taken a simple two-layer neural network. So, as is shown over here. So, this neural network has an output layer having only two nodes, and we also had an input layer which is also having two nodes, that is node 1 and node 2. In addition, we had another node which gives you the bias term, and we had an input layer. So, this was the hidden layer, and we had an input layer again consisting of two nodes, because we had two dimensional feature vectors x1, x2, but the number of nodes in the input layer was also 3, because we wanted to augment these input vectors by an additional term, by an additional component which is equal to 1, which takes care of the bias in every node. And there we have seen that the error that you compute at the output, so we had an error energy which was given by half of, say, your actual output xj, and because this was a second layer, so we put it as xj2 minus tj, take the square of this and sum of this for j is equal to 1 to 2. So, that is the sum of squared error that you compute at the output, and you take the gradient of this with respect to the weights between the hidden layer and the output layer, and accordingly by gradient descent algorithm you go on updating the weights of this hidden layer to the output layer. Then what we had seen is that whatever gradient that you get over here, you remember one thing that we discussed about, because this network is a multi-layer network. So, if my input is x, I have a function, say f1, which works on x along with an weight matrix or set of weight values which is a w1, and this output, this particular function is inputted to the next layer, which computes, say, f2 along with the corresponding weights w2. This again in turn inputted to the next layer, which computes, say, f3 along with the corresponding weights w3, and this continues, this goes on. And this is the final output that we get, assuming that it is a 3-layer network. So the output comes from the third layer, which is F3. So when I compute the error E is computed with respect to F3 and our target output. That is the target that we want to have. So here you find that this E or the error is actually available to F3 or F3, which is a function of, let us call this argument as theta 3. So actually error is visible to theta 3, but error is not visible to which was output of the input layer, which is the theta 1. Similarly, this one I call as theta 2. So error is actually visible to theta 3, it is not visible to theta 1. So if I want to compute the gradient of error with respect to W1, I cannot compute it directly. So what I have to do is, I have to compute the error with respect to theta 3, gradient of error with respect to theta 3, then multiply that with the gradient of theta 3 with respect to theta 2, multiply that with the gradient of theta 2 with respect to theta 1, and multiply that with the gradient of theta 1 with respect to W. So what I have to compute is, if I want to compute del E, say del W1, let us put del W1 ij, because the W1 over here is a matrix. So this will be del E del theta 3 into del E del theta 2 into del theta 3 del theta 2 into del theta 2 del theta 1 into del theta 1 del Wij1. So here you find that this product, that is del theta 3 del E del theta 3 into del theta 3 del theta 2 into del theta 2 del theta 1, these are the gradients which are being back propagated from the output layer to this input layer. And del theta 1 del Wij1, that is what is the local gradient. So to find out the gradient of the error with respect to Wij1, I have two components. One component is the propagated term, which is this, and the other component is the local gradient. So what we are doing is, we are multiplying the propagated gradient with the local gradient to get the actual gradient. Okay. So this is the same concept which has been applied over here, that whatever was gradient at the output, the same gradient when it comes over here, it is multiplied with the local gradient to find out how the error is propagated to the input side. And you remember one more thing, that every node in the hidden layer is feeding input to every node in the next layer, and that input is fed through a corresponding weight value. So when you are propagating error or the gradient in the backward direction, the gradient which is propagated from here through this and the gradient which is propagated through this, that will be weighted by the corresponding weight values and added over here. And this summation is, or the aggregate of the gradient which is collected at this hidden layer node, this is the total gradient which is available here through backpropagation. And this total gradient now has to be multiplied with the local gradient to find out what is the gradient of the output on this input weight, and accordingly I have to adjust these weight components, and that is what we have discussed in our previous class. So now let us see that how the same concept works in the node level also. So what we are going to consider now is backpropagation learning at node level. So let us see how it works. So to explain this, I'll consider a simple example. Let us assume the node implements a function, say f is equal to w plus x y into z. So, this is a function that this node computes. So, if I break or if I expand the particular node here in a hierarchical manner or in a staged manner, how this node actually computes this function, so that every function is broken into a smaller primitive set of functions. So, what I do is, you find that there are a few hierarchical levels. So, in the first level, you compute x into y through a multiplier block. So, this is a multiplier block which computes x into y. Then I have an addition block which computes. So, this intermediate variable x into y, that is assigned to an intermediate variable, so v. Then I have an adder block which computes w plus xy or w plus v, because v is the intermediate variable which is equal to x into y. So, this w plus xy is assigned to another intermediate variable u, and then finally, I compute f, which is nothing but u into z, or which is nothing but u into w plus x into y. So, this is my total node structure. And as we have discussed before, that every backpropagation learning algorithm is preceded by a forward pass. The forward pass, in which the functional value is computed, or coming to a network layer, given an input vector and whatever be the set of weights at different layers available at that point of time, using that you go for a feed forward pass, and in the feed forward pass you compute what is the output vector that you get. And if this output vector matches with the target, then I do not have any error. So, that means I do not have to go for backpropagation, I do not have anything to be adjusted, because whatever output I get, that is my desired output or the target output. But in case of an error, when the output does not match with the target, then I have an error, and the gradient of the error has to be backpropagated for weight adjustment. So, here also I have to have a forward pass. That means whatever be the value of x, y, z and w, using those values I have to compute what will be the value of f. And then if necessary, that means if the f that you get is not the desired value, then I have an error, and the gradient of that error has to be propagated in the backward direction for updation wherever it is required. So, now let us see how this forward pass actually works. So, to see how the forward pass works, let us assign values to w, x, y and z. So, we assume w has a value 5, x has a value 3, y has a value 2 and z has a value 4. So, accordingly, you will have v, which is equal to x into y, that gets a value 6. Then u, which is w plus v, or in other words it is w plus x into y. If you compute this, it will be 11. And then finally, f, which is u into z, or it is x w plus x y into z, that will assume a value 44. So, in the forward pass, I get the output to have a value 44, right. Now, let us see how the backward pass will work on this. So, to work on backward pass, see, what I want to find out is what is the sensitivity of output f, sensitivity of f on w. I want to compute what is the sensitivity of f on x, what is the sensitivity of f on y, what is the sensitivity of f on z. Or in other words, if I need any correction on f, suppose my desired value of f was something like 33, whereas I am getting a value of f which is 44. That means value of f has to be reduced. So, in order to reduce the value of f, whether I should increase value of w or I should also reduce value of w, whether I should increase value of x or I should reduce value of x, whether I should increase value of y or I should reduce value of y, whether I should increase value of z or I should reduce value of z. That is what is the sensitivity of f on w or on x or on y or on z. And this is what I need. I don't need how f varies with u or how f varies with v. That is not my concern, but my concern is how f varies with w, x, y and z. But I cannot directly compute del f del w or del f del x. The reason being, f is not directly visible to w, f is not directly visible to x, f is not directly visible to y. But yes, I can compute del f del z because f is directly visible to z. So, now let us see that how this gradient, in this case in the backward direction, can be computed again using the chain rule. So, for doing this, I assume the gradient that you get at the output is say 1. Then assuming this, how it is propagated in the backward direction. So, here what I compute is del f del z, and as I said, I can directly compute it. So, del f del z is nothing but, in this particular case it is u, and here what I have to compute is del f del u, and del f del u is nothing but z. Here what I need to compute is what is the value of del f del w. And as we said, because f is not directly visible to w, so I cannot really compute del f del w directly. So, for doing this, I have to make use of the chain rule. So, I have to make use of what is del f del u in this case, that has to be multiplied by what is del u del w. So, this is what I was saying, that del f del u is the back propagated gradient up to this point, and del u del w is the local gradient. So, you multiply the back propagated gradient with the local gradient to get what is del f del w. Now, similarly over here, I have to compute del f del v, but I cannot compute it directly because f is not visible to v. So, what I will compute is, I will compute del f del u and then multiply with del u del v. So, that is what gives me the sensitivity of v, sensitivity of f with respect to v, or the gradient of f with respect to v. Again over here, when I compute del f del x, first I have to compute what is del f del v, and then I have to compute what is del v del x. Similarly, over here I have to compute, in order to find out del f del y, I have to compute what is del f del v and then multiply that with del v del y. Right. So, here you find that your del f del u is equal to z, and what is del u del w? You come over here, del u del w is equal to 1, right. So, this will be simply the value of del f del u, which is nothing but z. Come over here, what is del f del v? Del f del v is del f del u into del u del v. And what is del f del u? Again, del f del u is equal to z. And what is del u del v? right. Del u del v, here you find that del u del v is again equal to 1. So, this value will simply be equal to z again. Coming over here, del f del x equal to del f del v into del v del x, and del v del x is nothing but y. So, del f del x will be y into z. So, this will be equal to y into z. Similarly, here as del f del v is equal to z and del v del y is equal to x. So, this will be x into z. So, you find that finally, following this backpropagation and the chain rule, I can find out what is del f del x, I can find out what is del f del y, I can find out what is del f del z, I can also find out what is del f del w. So, let us see that how we can implement this in modern programming languages. I will just put this because this is the kind of structure or the constructs which are given by modern languages meant for deep learning or machine learning implementations. So, first what you do is you set the input values. So, you find input values we had set earlier was w is equal to 5, x equal to 3, y is equal to 2 and z equal to 4. Then what we have done is we have computed the forward pass. In the forward pass, v is equal to x into y, then u is equal to w plus v, and then f is equal to u plus z. So, this is what we are computing in the forward pass, and then you have backward pass. So, in the backward pass, as we have seen earlier, that you see what we have done in the backward pass. Firstly, we have to compute del f del u, I have to compute del f del z, and then following the chain rule, finally I have to get what is del f del w, what is del f del x, del f del y, and so on. So, in the same manner, here you find out what is del f del u, which is nothing but z, and del f del z, which becomes equal to u, and then del f del w is nothing but del f del u into del u del w, that is what we had seen earlier, and we have also seen that del u del w is equal to 1. So, del f del w simply becomes del f del u. In the same manner, the del f del v also becomes del f del u. Del f del x becomes y times del f del v, because del f del x is nothing but del f del v into del v del x, where del v del x is equal to y, right. So, you simply come over here, you can look over here that del v del x is equal to y. So, that gives me del f del x or df dx is equal to y times df dv, and in the same manner df dy becomes x times df dv. So, after this backward pass, now we are ready with the sensitivity, computation of sensitivity of the output with respect to the inputs to the node. Okay. And the kind of graph that we have computed, this is what is known as computational graph. So, all these which are shown in red over here, they tell you that what is the sensitivity of f with respect to z, what is the sensitivity of f with respect to w, the sensitivity of f with respect to x, and sensitivity of output with respect to y. So, how does it help? Why we are doing all this? One is, we know that given a complicated function, how it can be broken into simpler functions to give you a complete node function, and then how we can write the backpropagation algorithm as well as the feed forward algorithms using the modern deep learning languages, the programming deep learning tools that we have. Right. So, this is simply same computation with the examples that we have shown earlier. So, here you find that your del f del w actually tells you that how f varies with w. So, if I increment W by say small amount, say for example 0.001. So, we had fed input W to be 5, now we make W to be 5.005. And as a result, you find that F has increased. In initially value of F was 44, now F has increased to 44.004. That says that by whichever amount we have incremented W, F has been incremented by 4 times of that. That means if I want to reduce W by varying reduce F by varying W, then W has to be incremented. And the same thing becomes true with all X, Y, and Z. And this graph is what is known as a computational graph. And now we find that what is the use of the computational graph, or how the computational graph helps you in writing such backpropagation algorithms. Right. We have few more examples in the same manner, but I tell you that some simple circuits, elementary circuits, using which you form or you design the complicated nodes. One is add, one is multiply, and other one is max. So, in the backpropagation, the multiply operation, as we have seen before, that if the output is say product x into y, then in the backpropagation, if the gradient up to this output is g, what you pass to the side of x is actually g into y, and what you pass to the side of y is actually g into x. Similarly, if it is summation node, then whatever is the gradient at the output side, it is simply copied to both the inputs. Similarly, if it is max, then whatever is the gradient at the output, the gradient is simply passed to the node of the variable which has maximum value. So, if x was maximum of the two, x and y, gradient g was passed towards x. If y was maximum, then gradient g would have to be passed to y. And using this, we can have we can represent complicated node functions using simpler partial differentiation or gradient operations, and that helps us to write the functions in a much simpler way, and that helps ultimately helps us to code the complicated functions. I will so this is the same thing, I will just skip that. This is again an example using that multiply, add, and max operation, and we had you can easily verify that how the forward pass information is propagated from input to output to get the final output, and then in the backward pass we can compute the gradients following the same gradient descent procedure. And I want to emphasize one more point over here, that in every case the gradient computation at a node is highly local in nature. As long as your gradient till the previous node, previous layer is computed, and that is fed to the current layer, in the current layer you can make use of the gradient which has been propagated to current layer, and all the computations in the current layer are highly parallel in nature. The computation of gradient of one node in the current layer is independent of the gradient computation in the other node. So, as a result, this entire function can be implemented in a parallel machine. If I have a parallel machine, then all the gradient computations of the backpropagation learning can be implemented using parallel operations. So, I will stop here today, and as we said, now onwards I will not consider the gradient learning anymore, or the gradient propagation or backpropagation learning anymore. For any application subsequently, I will simply use the term that the machine is learned or trained using backpropagation algorithm. Okay, thank you.